Welcome back. Last time we talked about polar coordinates without calculus. This time we will be combining polar coordinates with calculus. In particular, we'll be looking at some polar graphs, and we will ask some of the usual calculus-style questions. I am going to begin by talking about the problem of finding areas in polar coordinates. So let's review the basic idea from ordinary Cartesian coordinates, like you would have seen in an earlier calculus class. We typically have 2 points in the domain of the function, and the problem is to find the area of the region between those points and below the curve. Everybody knows the area turns out to be this integral. Everyone knows that, and I think most people taking this class will also have the intuitive sense of why that is so. It does not begin here. If at some point you have just memorized the fact that this area corresponds to this integral without any intervening steps, then you've missed something crucial. This comes from something much more basic. So let's review. The idea is that if we are going to find the area of this region with this curved boundary, the way we proceed is to think infinitesimally. That's the hallmark of calculus, after all. And in this particular problem, the problem of area, the idea is that we split this interval, AB, up into infinitely many infinitesimally small pieces. And on each one of those little infinitesimal pieces, we prop up a rectangle. And if we think of this region as being made up of infinitely many of those infinitesimally thin rectangles, then the idea is that we can find the area of a typical one and add them all up with an integral. So there's this process of disintegration, where we chop everything into infinitesimal bits. Specifically, we chop into bits that are really easy for us to understand and make sense of. And then the reintegration, where we integrate, we add everything all up again. So here, for example, the idea is that if I have this rectangle at a typical point x, I can get its area, as with any rectangle, if I know its width and its height. Well, its height is easy. If this is at x, its top is on the graph of this function, so its height is going to be f of x. And what about its width? Well, that is just an infinitesimal change in x. And an infinitesimal bit of x, we denote dx. So the area of our typical infinitesimal rectangle is the height times the width, which is therefore f of x dx. Thus, the total area of the shaded region is going to be, well, what do I do with this thing? I take these little bits of area, bring them down here, and what do I do with them all? I add them up. That's what an integral, a definite integral, is. It's a sum of infinitely many infinitesimal bits. And of course, I have to put the boundaries of integration on as well. I'm going to start my sum when x, the variable here, is a, and I will stop the sum. I'll stop summing these guys up when x, my variable, is b. And that's that. The notation is brilliant in that way, and it was Leibniz's genius in creating not just huge portions of calculus, but much of the notation that we use today, which does half your thinking for you. It was he, incidentally, who developed this familiar symbol right here for the integral, which he thought resembled a stretched out S for sum. Of course, he wasn't thinking in English. He was writing in Latin, so it would have been summa, but sum, summa, tomato, tomato, it doesn't matter. The important thing is that anytime you write down an integral like this, corresponding to an area, you actually understand what you are doing. I'm not talking about the process of integration, just what this is capturing. That you are summing up a bunch of little areas of this form, those rectangles. When we move over to polar coordinates, the integrals we do for area will take a different form. And if you understand the idea, you're breaking something up into infinitesimal bits, look at the area of one infinitesimal bit, then add them all up with an integral, then everything is very, very easy. Now let's consider the analogous situation with polar coordinates. Instead of the situation here, where we let x, the independent variable, go from a to b, and we looked at the area that was swept out as a result, here the independent variable is theta. So if we imagine theta going from some angle, let's call it alpha, and we sweep out until we get to some other angle, which we'll call beta. Well, we end up cutting off a certain amount of area, and we would like to come up with an expression for that area. Now, the general spirit of the problem is going to be the same here as it was here, but the geometry is slightly different. In the classical case, we start at some typical value x, and we let that independent variable x increase by an infinitesimal amount dx. We end up generating an infinitesimally thin rectangle. Well, we're going to do something similar here, except that our independent variable is no longer x, it's theta. So if we start at some typical value of theta, first of all, we have this slanted line rather than this vertical one. But now if I increase theta, I nudge it forward by an infinitesimal amount, what am I doing? I'm not traveling along the x-axis like I was before. I'm increasing this angle by an infinitesimal amount. So I would end up with this little wedge. Obviously, this is greatly exaggerated. It's supposed to be an infinitesimal angle. Let me pull that out separately. Okay, there's my wedge without some of the distractions. That angle right there, that's d theta. That's the infinitesimal increase in angle, d theta. And now, just as on this first case, I knew the height of my rectangle was f of x, because it goes from the x-axis up to the graph of y equals f of x. Here, I know the length of my little wedge. It's going from the pole out to the curve r equals f of theta. So if this is at theta, the length of my little wedge is going to be f of theta. And from here, the rest of our analysis is structurally identical. To come up with the area of the shaded region, I'm going to figure out the area of a typical infinitesimal slice. And then what am I going to do with those areas? Obviously, I'm just going to slap an integral sign in front of it. But a typical slice here is not a rectangle. The area of one of these is not f of theta d theta. This is not a rectangle. It's a little wedge, or as I call it in the book, a pie slice. A very, very tiny slice of pie, an infinitesimally thin slice of pie. So now the problem is reduced to finding the area of this little infinitesimal wedge. Now, how do we get the area of a wedge? Well, we are thinking of it as a little slice of a larger pie. A piece of a circle whose center is the pole, that's the full pie, and this is a little slice of the pie. Now, how do we find the area of a slice of pie? I would like to think that you remember this from a previous class, and maybe you do, but maybe you don't. So just to make sure we're all on the same page, let me come over here and do a little scratchwork review. This is an important problem. This is fundamental geometry. It comes up in lots of places. If I have a circle and I have a little wedge of that circle, the angle doesn't have to be infinitesimal. It can be any old thing. In fact, let's call it, let's see, I used theta and alpha. How about, let's call it phi. If the angle of this little wedge is phi and the circle has radius r, what's the area of that wedge in terms of r and phi? Just think in terms of proportion. First, what's the area of the entire circle? Well, that's easy. That's pi r squared. That's the area of the full circle. But of course, we just have some fraction of the circle. So we're going to have to multiply that by whatever fraction of the circle we have. This angle right here, phi, what fraction does it take up of the full rotation? So it's going to be phi to the full angle. Well, what's the full angle? That's 2 pi. Provided we are working in radians. This is one of the reasons we like radians. It makes our formulas simpler. If we were working in degrees, we would have to put 360 down here. Anyway, these 2 pi's cancel out, and I'll rearrange these a bit. I've got a half, then an r squared, and then my angle, phi. So half r squared phi. That is the area of that circular wedge, that pie slice. Now, this is one that everybody should know who uses mathematics. Very important formula and easy to derive. If for some reason you ever forget it, you should be able to scratch it out just by thinking of this picture in less than a minute. Anyway, now that I've reminded you of it, we can put it to use in our original problem. So we have this region swept out by our polar curve. We're going to break it up into infinitesimal pieces. We'll get the area of a typical piece, and from that we'll be able to get the area of the whole thing by integrating. So we need the area of a typical infinitesimal wedge at theta. Well, it's a slice of pie. What's the area of such a thing? We just saw it's half the square of the radius. Well, what's the radius? F of theta times the central angle of the wedge. Well, what's that? That's d theta. And now we've got it. Thus, the total area of the region is, well, it's the sum of all those infinitesimal wedges areas. So we take this guy, a typical one, and add them all up, starting when theta, the independent variable, is alpha, and stopping when our independent variable theta is beta. And at this point, we've just reduced the problem to a typical integral calculus problem. Find the antiderivative of all this stuff, use the fundamental theorem, and we're done. Now, a word of caution. Do not memorize this. Do not even memorize this. Just think your way through, step by step. Do memorize this if you do not know it already. It is fundamental. It comes up everywhere there are circles, or things that can be approximated by circles. In contrast, this is not fundamental, and therefore this stuff is not fundamental. Yes, I know, you're taking a calculus class where you're going to have to solve lots of problems involving those things. You will have to solve questions about areas like this. But don't memorize these things. It does you no good at all. This does you a lot of good. Memorize it and understand it. It's very easy, and then you can apply it all over the place. This is an artificial problem to help you develop an instinct for working with calculus and for working with polar coordinates. You need to develop those instincts by building those integrals up step by step, by thinking about them. Memorizing dopey formulas like this is not going to help you. I mean, it'll help you pass a test, but it's not going to help you learn calculus. And presumably, you are going into some academic field, some profession, where you will need to use calculus, where you will need to think in terms of calculus. That is not going to involve applying memorized formulas, unless they're really basic ones that everyone should know, like this. All right, so now a few of you may be irritated and say, well, how am I going to do this if I don't memorize it? Let's do a concrete example. Let's go back to this crazy graph we were looking at in the last video, the graph of r equals 1 plus sine 2 theta. We spent a good long while figuring out what its graph looks like, so let's go ahead and make use of it. Let's find the area of that shaded region. Okay, what are we going to do? We're going to think our way through it. We've got this weird curved region. We're going to break it up into infinitesimal pieces where each piece is simple. The curve here is given in terms of a polar function, and it's swept out by a rotating ray. Well, I will break it into little infinitesimal wedges. What's the first thing I'm going to do in any find the area problem that involves calculus? I'm going to draw a typical slice whose area I will find and then integrate. In this case, a typical slice, which I get by nudging the independent variable theta forward a little bit, might look something like this. And now just by thinking about my little piece, I can more or less sleepwalk my way to the integral I need. The area of a typical infinitesimal wedge is, well, what's it going to be? Well, we recall our fundamental formula, our basic geometry. The area of this guy is half the square of the radius times that central angle. Well, what are the radius and central angle on something like that? Well, the radius is that length right there, which is r for any given theta, which we know is 1 plus sine 2 theta. And that central angle is just our infinitesimal nudge, d theta. So the area of our typical infinitesimal wedge is going to be half the square of the radius, that stuff, 1 plus sine 2 theta, times this central angle, which is d theta. So this expression gives me that infinitesimal bit of area taken up by the infinitesimal wedge, and there's one of those for every value of theta as I go from here, where theta is pi over 2, to somewhere here, where theta is... How would we figure out what that is? We wouldn't just look and say, well, it looks like 142 degrees to me. No, we could figure it out exactly by thinking about the equation. Whatever angle it is, I know that r is 0 right there, which means that it's time for a little more scratch work. When r is 0 in that equation, what is theta? And this is not only scratch work corner, this is trigonometry review corner. How are we going to solve this sort of thing? Let's push the 1 over there, and we have sine of 2 theta is minus 1. Well, forget about the fact that it's 2 theta. Just think of it as a red box there. Sine of whatever is minus 1. Well, sine of what is minus 1? Think of the unit circle. Think of the definition of sine. As I have this point moving around, the sine is the second coordinate, the y coordinate. When is that minus 1? Only when that point is down here at 3 pi over 2. So the stuff in my red box has to be 3 pi over 2. But the stuff in the red box is 2 theta, so that means theta has to be 3 pi over 4. Good. And just as a quick check, if we stick 3 pi over 4 in this, that becomes sine of 6 pi over 4, which is sine of 3 pi over 2, which is indeed 0, as we said. Okay, good. We've got it. So if that's the area of a typical wedge, we can get the total area of the region by integrating this guy. So the total area is the integral of this stuff as theta runs from pi over 2 to 3 pi over 4. And now we just have to do this integral, which is a matter of finding the antiderivative of this function. The Math 153 portion of this problem is in a sense over. Now you are thrown back purely to a Math 152 problem. Come up with that antiderivative. I have a feeling some of you will need a review here though, and that is perfectly fine, so let's go ahead and do that, lingering as usual over the trigonometric parts. So, of course, I can pull this factor of half through the integral, and I'm going to need to expand all this out because there's no obvious way to integrate it as is. When we do those two things, we end up with this. Is this an integral you know how to do? The answer should be yes, but let's review. We know that the integral of a sum is the sum of the integrals, so we'll ultimately end up just integrating term by term. So let's think about each term. Obviously, the first one is trivial. Its antiderivative is going to be theta. The second term, I hope you see, is very doable. If you really must, you could do it with a u substitution, although at this point in your career, you should be able to do it just by staring at it, thinking of a prospective antiderivative, and making some adjustments as needed. I mean, just to convince you that this is easy, let's think of an antiderivative of this thing on the fly. Well, the core of this is the sine function. So we know that the antiderivative is going to be something involving a cosine, right? Well, not quite right, because if I take the derivative of cosine, of course, I end up with a minus sign. Well, I don't have a minus here, so I need to balance that out in my antiderivative. Let's just put a minus there. Haha, that'll take care of it, because now when I take the derivative of minus cosine, I will get minus sign, which is a sine. Okay, that's a good start. But minus cosine of what? Well, I've got a 2 theta in the thing I'm aiming at. So what if I just started with a 2 theta here? Okay, well, if I took the derivative of that, I'd get sine of 2 theta, but I'm not done. I have to do the chain rule. I have to take the derivative of this stuff on the inside, which delivers a 2 out front. Hey, that's looking good. That's actually the function I'm aiming at. So when I take this integral later, I'll know that the antiderivative of this is just minus cosine 2 theta. Anyway, that was just to convince you that this one is also easy. It's this third term that might throw people off. Integrals of this form, where we've got the square of a sine or square of a cosine, come up pretty frequently in these problems, which means that it is time for some more trigonometry review. What are the trig identities that come up over and over and over in integrals that you should have memorized? There are only a handful of them. Two of the most obvious ones that hopefully you already have packed firmly into your head are the double angle identities for sine and cosine. Sine of 2 theta turns out to be 2 sine theta cosine theta. And that one is very easy to remember because it sounds like a line of poetry. 2 sine theta cosine theta. And the double angle identity for cosine tells us that the cosine of 2 theta is cosine squared theta minus sine squared theta. Another one that's pretty easy to remember, in part because this looks so similar to another identity that you certainly know, the Pythagorean identity, which tells us that cosine squared plus sine squared is 1. These three identities should be firmly etched into your mind. Now, why do I mention these? It's not just to review some fundamental identities. I want to focus on the similarities between these two identities, the double angle identity for cosine and the Pythagorean identity. It turns out that if we manipulate these equations a little, we end up with a pair of other identities, which are often very, very useful in integration. So we start with these two very similar looking identities, at least on one side of the equation. If I add the corresponding sides of the equations, what do I get? Well, on the right-hand side, I get some cancellation. When I add these guys, the sine and the minus sine squared cancel out. And instead, I'm left with 2 copies of cosine squared. And then when I add on this side, of course, I get 1 plus cosine 2 theta. Well, if I divide both sides of this equation by 2, I get this, which is a very nice identity for cosine squared. I'm going to record it over here. This identity is very useful in integration. For example, even if we just wanted to integrate cosine squared, how would we do that? We would use this identity, and now we would have it like that, and now it becomes an easy integral. But anyway, that's not all. This is a great identity for cosine squared, but there's a similar one for sine squared. And the really nice thing is that it comes from the exact same place. The only difference is that instead of adding the corresponding sides of these equations, which gets rid of the signs, I'm going to subtract corresponding sides of the equations. That'll get rid of those cosines, leaving me with an identity for sine. So when I do that, well, let's see, on the right-hand side, if I subtract this stuff from this stuff, I get cosine minus cosine is 0, minus sine squared is minus 2 sine squared. I guess this would have been cleaner if I subtracted this equation from this one, but no big deal. It'll all wash out in the end. And over on this side, I get cosine 2 theta minus 1. Well, if I want an identity for sine squared, all I have to do is divide both sides by minus 2. When I do that, I will end up with this, but that's a little ugly because of this negative. So let's multiply top and bottom by minus 1 to clean it up. Of course, that'll give me 2 on the bottom, and on the top, when I multiply something of the form a minus b by minus 1, it becomes b minus a. So the top will become 1 minus cosine 2 theta, and thus the whole thing will become this. And now I have a nice identity for sine squared. I'm going to put it over here as well. These two identities go by different names. I know them as the half-angle identities, which I don't think is a very good name, frankly, in part because there are other identities which are sometimes called half-angle identities. The idea is that this angle is half of what you get on this side. But call them what you like. I will continue to call them half-angle identities for better or for worse. You should know them. Hopefully you learned them in your previous course on integral calculus, but times being what they are, you may not have. Fortunately, these are very easy to memorize because they have almost the exact same form. Cosine gets the plus and sine gets the minus. Get them in your head because they're very useful in integrals involving trigonometry, and we'll be seeing a lot of them in this chapter. The other nice thing about these identities is if you happen to forget one, if you're taking a test and you think, oh my God, I cannot remember that stupid half-angle identity for cosine squared theta, what is it? It's very easy to derive it. I've erased my scratch work previously, but you just take those two identities that look so similar, the double angle identity for cosine and the Pythagorean identity, add the corresponding sides or subtract the corresponding sides as you need to, and these identities fall right out. So memorize them, but also know where they come from. All right, we're going to get to use them, or this one anyway, because the integral we were working on involves a term that's the sine squared of something. So I'm going to take this one that I'm going to need, and maybe I'll hide it in the corner. Okay, there's my secret weapon that I'll bring out when I need it in a few minutes. It should be in your head, but I'm keeping it there for a few minutes for those who don't have it in their heads yet. Anyway, let's get back to our integral. We were trying to find the area of this region, so we broke it up into infinitesimal pieces. Those were little wedges. We found the area of a typical wedge using that usual old formula. We added all those up as theta ran from pi over 2 to 3 pi over 4, and that gave us this integral. We expanded this out, and now we still need to do the integration. We recognize that this term has an easy antiderivative, this term has a pretty easy antiderivative, but this one could give us trouble if we were not prepared with our half-angle identity, which we know is what we use to integrate good old sine squared when we see it all by itself. You shouldn't make that too reflexive because sometimes you might have a sine squared and a cosine squared that can combine into a 1, or if there's a minus, into a cosine of double the argument using the double angle identity for cosine. But anyway, in this case, we don't have anything like that. So yeah, we're going to use this half-angle identity. And if I do that, I'm going to bring all this stuff down, but this sine squared 2 theta, I'm going to expand that out using my half-angle identity. Now I know that sine squared of something can be written in this way. Oh, and I don't want you to be distracted by the fact that I've got a theta here and a theta here. This is just the general formula. So maybe I'll replace those thetas by black stars. Why not? Sine squared of anything, any old black star, is 1 minus cosine of double that anything, double that black star, all over 2. So that means this junk is going to become 1 minus cosine of what? Well, this guy gets doubled in the identity. So this 2 theta becomes 4 theta, and all of it is divided by 2. Good. What next? Well, we know we can get the antiderivative of this and this. What about this? Is this any easier? Yeah, let's break this into 2 fractions. Okay, that's better. Oh, and let's combine this 1 and the 1/2, those 2 constants. If I bring him over here, we get 3/2. And now let's go about finding the antiderivatives. Okay, I'll bring that half down. Antiderivative of 3/2 is, of course, 3/2 theta. Antiderivative of this, well, we scratched that out before, so I'm just going to go ahead and write it down. That's minus cosine 2 theta. And now how about this guy? We should be able to do the exact same trick just by thinking about an antiderivative, making adjustments in our mind until we get it right. So let's try that. we're trying to find a function whose derivative is this. Well, that's clearly going to involve a sign if we're going to end up with a cosine there. But we have a minus in there as well, so we should have something like a minus sign. I'm just doing my scratch work over here. What about something like minus sine of 4 theta? Because we obviously need to get a 4 theta in there. Well, if I took the derivative of that, I'd end up with what? Cosine, but yeah, minus cosine of 4 theta. Oh, but then I'd get the 4 from the chain rule, so I get minus 4 like that. The derivative of this gives me almost what I want. It's only off by a constant multiple, giving me a minus 4 where I want a minus a half. I want to divide this sucker by 8. Oh, well, I know how to do that. Just divide this by 8. So make that minus an eighth. So I'll put that in here, and we have our antiderivative. Of course, we have to now evaluate at pi over 2 and 3 pi over 4. Let's see, when we start here at 3 pi over 4, I pop that in, and that'll give me 9 pi over 8 minus, pop it in here, and I get cosine of, what is that, 6 pi over 4, which is cosine of 3 pi over 2. Well, what is that? Think about the unit circle. 3 pi over 2, what's the cosine there? Is 0, so I don't get anything. And then when I pop this in here, I get sine of 3 pi, which is another big fat 0. So I'm not even going to bother putting that term in. And now I have to pop pi over 2 in all of these. Subtracting those off, in the first term, that's going to give me 3 pi over 4. Then I will subtract. This is going to become cosine of pi. Cosine of pi is minus 1. So I'm subtracting minus 1, which means I'm adding 1. And then in this last one, I put this in here, and I get sine of 2 pi, which is 0, so I don't get anything. And now I just have to do some arithmetic. And when I do that, I get half of 3 pi over 8 minus 1, or if you like, 3/16 pi minus a half. And this is an area, so maybe I should say that this is that many square units. And at long last, we have it. We have the area of that thing. I told you there'd be a lot of trigonometry in this chapter, so I hope you are brushing up on it and that the review is helpful. And again, I want to emphasize how important it is in setting up a problem like this one, in thinking your way through it. Do not memorize some silly formula that you find in some crappy book online. There are important formulas to memorize in mathematics. We have encountered many of them in this very lecture. And then there are things that are not so important to memorize, often because you can recover them just by thinking about it. When you go through the process of thinking about how to set up this initial integral, you are reviewing all sorts of important things. You're reviewing that fundamental formula about the area of a circular wedge. You are reviewing the crucial idea of what an integral is by chopping something up into pieces, analyzing the individual pieces, and then adding them all up, and so on and so forth. So if you have developed bad mathematical habits in the past, well, that's unfortunate, but you still have time to change them. So please get working on that. You'll find some further examples of computing areas in the book, and of course you will have some homework problems about them too. Just bear in mind what you're doing when you set them up, and all will be well. For example, if you are looking at a situation where you have two polar curves and you want to find the area cut off between them, you don't have to go scrambling for some new formula. You just think your way through. How do you chop that up into infinitesimal bits? Well, as you are rotating this ray, you're still getting infinitesimal pi slices, but in this case, you don't want to keep the entire slice. You just want a bit of it. So what are you going to do? Well, of course, you can find the area of the full slice, and then find the area of this stuff that you want to throw away, subtract the blue stuff from the full slice, and then you will have a representation for the infinitesimal area of one of these little pieces. Get a typical one, add them all up, and you've got it. But enough of that. Let's move on to a new kind of problem. Let's talk about slope. So let's suppose we've got some kind of a polar curve, r equals f of theta, and at some point on the curve, we want to know the curve's slope. How will we find it? Well, we just have to go back to remember what is actually meant by the slope of a curve at a point, because you might say, wait a second, only lines have slopes, not curves. Well, recall the idea. If we look at an infinitesimal neighborhood of the curve around a point and zoom in on it, we will find that locally the curve is straight. That's the key geometric insight that underlies all of differential calculus. So since the curve is straight on an infinitesimal scale, it makes perfect sense for me to talk about slope here. At a point, it makes perfect sense to talk about the slope of a curve locally, even if it doesn't have a global constant slope the way a straight line does. And going back to what you learned in elementary algebra, slope is just rise over run, change in y over change in x. Well, it's the same story here in our infinitesimal microscope. If we change the x coordinate by some little bit, dx, we get a corresponding change in the y coordinate, dy. So the slope is once again just dy over dx. And if we take this line that the curve coincides with on an infinitesimal scale and extend it, of course, what we end up with is the tangent to the curve at that point. It's the exact same line. It's just that here we're seeing it where it coincides with the curve, and here we're seeing it from a larger perspective where it separates off. But it is the same line, and therefore it has the same slope, which is still plain old dy over dx. So you might be tempted to say, oh, well, that's just the derivative. So to find the slope, I just take the derivative of this thing, right? No, that's not right, because this is specifically the rate at which y changes with respect to x. The variables here are not x and y. They are describing very different things. Dx describes a horizontal nudge, and dy is the corresponding vertical change. If we just took the derivative of that thing, we'd be looking at dr d theta, which is very different. The situation there would mean we are changing theta by an infinitesimal bit, changing that angle and seeing how r, the distance from the origin, changes in response. That has nothing to do with horizontal nudges and vertical changes coming in response. So this expression is not going to help us compute slope. We can still get it though, and very easily, just by remembering that slope is dy dx, and then playing some games with the Leibniz notation. This will be yet another demonstration of how brilliant this notation is. Slope, we said, is going to be dy dx, purely on basic intuitive geometric grounds. Fine. But if our function is given in polar coordinates, we don't have y as a function of x. We have r as a function of theta. Well, to inject theta, our actual independent variable here, into the slope, we're going to do a simple trick. Take this dy dx fraction and divide top and bottom by d theta. Now, instead of looking for the derivative of y with respect to x, we've got at least y with respect to theta and x with respect to theta. In fact, let me rewrite this again, like so. I think it will be easier to understand what follows if we write it this way. Well, the thetas are dandy, but you might reasonably say, well, look, I don't have x and y as functions of theta. I have only r as a function of theta, so how am I supposed to take these derivatives? And this is where we remember our conversion formulas. I know how to write y in terms of r and theta. That's r sine theta. And of course, x is r cosine theta. And here's an instance where those conversion formulas are really helping us. Well, now this is looking a lot better because we have that the slope is equal to this ratio of derivatives with respect to theta, and I've got some thetas in there, but I also have this r in there. I'm going to have to do something about that. I need to write it in terms of theta. Oh, but that's no problem because we have r explicitly as a function of theta. If I substitute that in, then I get this. And now I'm in business. What's the slope here? Well, the slope is equal to this particular ratio. And the stuff on top and bottom, these are things I can compute. This is a function of theta, so of course I can take its derivative with respect to theta. This is a function of theta, so of course I can take its derivative with respect to theta. And now the problem, at least in this abstract dumb show, is solved. We could actually spin this out a little further, using the product rule here and so forth, but there's no need to. Please do not memorize this expression, or what would follow if you took the product rule there. It will do you no good at all as far as learning calculus is concerned. This little chain of equalities, on the other hand, which only takes a minute to run through, does you a lot of good. It reminds you of what slope is. It allows you to appreciate the brilliance of Leibniz notation. I mean, try making that step with like prime notation for derivatives. With Leibniz notation, it's a piece of cake. It's obvious. It helps you see those conversion formulas in action. And then finally, it's a matter of just cranking out some derivatives. But if you just memorize a formula and then just crank out derivatives, you're not actually learning any of those important lessons that carry over into much wider domains. I think you would be hard-pressed to find a single living mathematician who knows a formula for the slope of a curve in polar coordinates by heart. If he or she needs it, then that person is just going to think their way through this process. And you should too. Let's do a concrete example. We're going to find the slope of this polar function where theta is pi over 6. This is roughly the graph of that function. You could find it in the usual way with a Cartesian blueprint, but I don't want to waste time with that right here. So we'll assume that's been done already. We've got our graph. And when theta is pi over 6, we're looking at a point somewhere around here. So before we even get started, one thing is obvious. We're clearly looking at something with a positive slope. How steep the slope is hard to tell because my graph, of course, is very crude, but we will be able to calculate it exactly. Let's do so. Without having memorized anything, we know that the slope is dy dx, but we don't know how x and y are related on this graph. We only know how the polar coordinates are related. So we need to inject polar coordinates into this picture. We do so using the trick I described a moment ago. Divide top and bottom by d theta. Now we've got theta into the picture, and let's pull the y and x down from their perches, like so. Now we'll apply our conversion formulas. X is our cosine theta, y is our sine theta. Finally, since we are itching to take derivatives with respect to theta, we need to convert these r's over to theta, which of course we can do using the equation of our graph. Where we had r's before, now we have sine 2 thetas. And all this stuff is something we can compute, because this is just a function of theta, and we want to take its derivative with respect to theta, and same story downstairs. When we do so, we get this stuff, which just comes from applying the product rule upstairs and the product rule downstairs. And this somewhat gory recipe gives us the slope of this curve as a function of theta for any value of theta. So in particular, when theta is pi over 6, the curve slope is, and now all we have to do is stick pi over 6 into every one of these thetas. That's a bit of a pain, but when we do so, we get this, which tidies up pretty easily. The 2 and the half cancel each other out. Same story downstairs. And I won't bore you with the rest of the arithmetic, but you should find that it comes out to 5 over root 3, which is a pretty steep slope. Square root of 3, as everybody knows, is about 1.7-ish. So that goes in here more than 2 times. So the slope here should be greater than 2, in fact, which gives a pretty good indication of how inexact my drawing is. Anyway, that's about all there is to computing a slope in polar coordinates. Let's do one more quick example. Let's find the slope of a particularly simple equation, r equals theta, where theta equals pi over 2 and where theta equals 5 pi over 2. Now you might be tempted to say, well, isn't that solving the same problem twice? I mean, theta equals pi over 2, that's just a right angle, and theta equals 5 pi over 2, that's 5 right angles. So a full turn and then another right angle. It takes you to the same place. Shouldn't it be the same then? Not really. It's true that when you rotate a ray pi over 2, it ends up in the same position as if you rotate a ray through 5 pi over 2. But we're not just interested in the position of the ray. We're interested in the position of that point that moves on the ray as it rotates. And while the ray may be in the same position at pi over 2 and 5 pi over 2, the point can be at very different locations on that ray. And the curve passing through it could look very differently in those locations. But we can see this very easily in this specific curve, r equals theta, which I believe I graph in the book. We can graph that just by thinking about it. When theta is 0, r is 0, so we start at the pole. And as theta increases, as the ray rotates, r, the distance from the pole, increases as well. By the time we've gotten to pi over 2, its distance from the pole is pi over 2. By the time we've rotated to pi, its distance from the pole is pi, so that would be twice as far away. By the time we get to 3 pi over 2, its distance from the pole is 3 pi over 2, so that's going to be 3 times as far away as it was in the first spot we considered. By the time we get back to 2 pi, well, now it's 4 times as far away. And we see what's happening. We end up with this spiral that keeps widening as we go. So if we want the slope when theta is pi over 2, we're looking at this point right here. Whereas if we're looking for the slope when theta is 5 pi over 2, well, I'm afraid I'm off the screen, but this is happening at a different point. So the slope could be slightly different. In fact, it will be, as we see. All right, anyway, how do we solve it? Same way we did the last one. Nothing to memorize, just think. The slope, of course, is dy dx. Divide top and bottom by d theta to get it into the picture, since our curve is given in terms of theta. Well, that's the same as derivative with respect to theta of y, which is r sine theta. And this is the derivative with respect to theta of x, which is r cosine theta. And now I need to eliminate these r's so that I can get the stuff in parentheses completely in terms of theta, because then I'll be able to take those derivatives. How do I do that? Well, I know what r is in terms of theta. R is theta. So making those changes gives me this stuff. Instead of r sine theta, I have theta sine theta. Instead of r cosine theta, I have theta cosine theta. Now I just have to take the derivatives on top and on bottom, and I end up with this, thanks to the product rule. And now I have the slope of the curve at any point as a function of theta. So in particular, when theta is pi over 2, the slope is, well, now I just have to pop pi over 2 into this thing, and I get, this one's not nearly as nasty as the other one, because this term and this term disappear, because cosine of pi over 2 is 0. So upstairs, I'm just left with 1, and downstairs, I'm left with minus pi over 2, so this becomes minus 2 over pi, which at least looks plausible on my bad drawing, since minus 2 over pi is in the neighborhood of minus 2/3. Moreover, when theta is 5 pi over 2, the slope is, well, now we just have to pop 5 pi over 2 everywhere in there. And let's see, we get 1 again upstairs, but downstairs now we get minus 5 pi over 2. So the whole thing comes out to minus 2 over 5 pi. So still negative, but closer to 0 because this denominator is larger. So maybe something like this. And it's not hard to see that each time you wrap around, that slope is getting closer and closer to 0. It's always negative, but it's approaching 0 in the limit. All right, that's about all I have to say about slope in polar coordinates. I hope one of the things you take away from these sections on polar coordinates with calculus is not just that some of the calculations are gory, which is true, but that all these little pieces come together that you understand already. And it's not just new mysterious formulas handed down by God for you to cram into your head and then reproduce on a test. Trying to learn those things that way is actually counterproductive as far as learning mathematics and learning to think mathematically, and in particular, learning to think in terms of calculus is concerned. So please don't do that. Anyway, we will be seeing something similar in the next sections of the book and in the next couple of videos, which are about parametric equations, both without and with calculus. When we get to the calculus stuff, everything is going to be about thinking our way through it, making good use of that Leibniz notation, and not just memorizing formulas. So, you have that to look forward to. I will see you then. Good day, good night, goodbye.